Next, we have a talk on transversability mapping with OpsLam 3 on ROS2 by Suchetan Saravanan from Clutterbot Technologies.
Good afternoon. Let's get started. A little over a month ago, I had the brilliant opportunity to present this at ROSCon Global. Well, that was a lightning talk, and I'm so glad that I can finally present this in much greater depth for all of you today. How do I? Okay, so a little bit about myself. I'm Suchetan. I'm a robot software engineer at Clutterbot, and my interests are SLAM and navigation. Over the next 20 minutes, I will be covering two topics. First one is how you can use OpsLam 3 with ROS2, and the second one is the most important part, that is how do you actually build a 2.5D map using your SLAM. So we all know that OpsLam 3 is a very widely used SLAM algorithm, and needless to say, it's absolutely amazing. But there's one thing wrong about it. It's not wrong, it just doesn't exist, and that is the ROS2 support. So the original ROS interface that was given on the OpsLam 3 wrapper just provides very few features. You can just input your image and you can get back the output. It doesn't even publish the robot TF. And this is the library that I'm going to show you solves that problem. Now, before we get started, we obviously have to know how OpsLam 3 works. It's basically a visual SLAM algorithm, a very famous one, and at the very core, it uses OR feature descriptors in the sense that it detects features in your incoming image stream, and it looks at how they change over time, over multiple frames, and then therefore estimates the pose of your camera. Now, there are a few things to note here. The feature descriptors, or the features that last over a couple of frames or even a bunch of frames are marked in memory as landmarks, and every few frames, OpsLam 3 decides that, okay, I want to use this frame as a keyframe. And these keyframes are also stored in memory, which help with localization. Now, all of this obviously doesn't matter for a person who just wants his localization sorted and he wants to move on with his life. And that's where this package helps you. Well, for starters, obviously it publishes the robot TF, which doesn't exist in the original integration. And apart from that, it has a lot more. It publishes the stored landmarks, the keyframes, and a lot of SLAM information. And you can also get the current FOV and the sliding windows directly published into RViz with this wrapper. Apart from that, a full post graph visualization using marker arrays and also removal of this power-hungry OpsLam 3 visualizer directly into RViz is coming very soon. Now, obviously, I'm not showing you a wrapper that just aids visualization. It does a lot more than that. So for those of you who know, OpsLam 3 is a multi-map SLAM in the sense that when you lose tracking, it resets the pose to 0 and creates a new map. And when it detects common features between these two maps, it merges them seamlessly and you can restore your tracking. But when you use it in a commercial sense, obviously this doesn't work because all of a sudden, if your pose is reset to 0, you don't know where you are in the original environment, and this is a big issue. At these stages, you need to shift to your onboard odometry and then restore the tracking when it's back. And this does that for you. When you use this wrapper, it seamlessly switches between the onboard odometry and the OpsLam 3's tracking pose whenever it's needed, and you don't have to worry about it. There's a lot more features that it offers. You have services to get the covariance, the maps in picture, the keyframes in picture, and also you can slow down or delay loop closures if you want. You can add external deliberate keyframes if you want, and also, obviously, save and load maps through ROS service calls. It's Dockerized and runs on ROS2, so it's very easy to use, and you can pull it today and run it right here, right now, if you want. Now, the guy who wanted his localization sorted is finally happy, and he can run OpsLam 3 on ROS2. And an important thing to note here is that OpsLam 3 has been unmaintained for a couple of years now. The authors released it, published it, and it's gone unmaintained. It's received hundreds of PRs from the active community, and those fixes are spanned across different folks and different clones and whatnot. It's across GitHub. I've tried my best to incorporate not all of that. It's a very big job, but at least what I found relevant into this wrapper, and you can try it out if you want. Now, I'm trying to get this to 200 stars, guys. Just please star it. Okay, our robot is localized. What about the map? The map, obviously, I'm not talking about the landmark map. I'm talking about an actual map which you can navigate in, a 2.5D or a 3D map which you can use to map your environment. So, when I talk about the map, I mean traversability map. In the sense, you estimate the risk of traversing an environment on the fly and in real time. Now, why is this important? It's because in more or less, in all of the cases, at least in classical sense, your global plan and your local plan is directly dependent on your map. And the representation you choose is of utmost importance because that's the way your robot avoids the environment. And so now that we know why the representation is so important and why that plays such a big role, let's have a look at one of the examples. So this work was done at Issy-sur-Perrot in the south of France just about a year ago in my thesis. And the core idea behind this is that it's a local traversability scheme. The robot's moving in an environment, and you can see the image overlaid on a traversability map. The blue ones are actually traversable, the red ones are not, and the green and yellow ones are slightly traversable. Now, this was done on an Ooster 128. Please let me bring that to information here because this doesn't need an actual such a dense point cloud to run. An Ooster 128 is very dense, but it will run just fine on your VLP16 or any other standard 3D LiDAR. So how do you actually estimate your traversability? You have your incoming point cloud stream. You convert that to your map frame. Oh, sorry, there's a mistake there. You convert that to your baselink frame from your sensor frame, and then compute 3 different hazards. These hazards basically signify how much is the risk of traversing an environment. The first one is the step, the second one the pitch, and the third one is the roughness. I'll get to this in a bit, and I'll explain much more detail about how you compute these, but let's move on. Once you've computed these hazards, you pass them to a traversability node, and finally you have your local map. And this local map is obviously an occupancy grid, which you can feed again to your controllers. Now, when you have an incoming point cloud stream, it's important to filter it. And there can be a bunch of outliers in your incoming stream, and that can cause a lot of issue with your traversability estimation. So first of all, you filter the outliers, and then you build them onto a grid. Now, this grid, you can choose your resolution. It's all parameters. And once you have the grid, you can carry forward with your hazard computation. The first one's the step hazard. Obviously, when your robot's moving in an environment, you need to estimate the ground clearance properly. The ground clearance is defined as the step over here. And the higher the ground clearance, the higher is the hazard. Then you need to also estimate the pitch. The more slopey your surface, the more likely it is that the robot is going to slide off. And finally, in my opinion, the most interesting one is the roughness. This signifies how bumpy your ride is going to be. So you have an incoming point cloud. First of all, you try to fit a best fit plane in every nearest neighbors, and then you find how much your point cloud is deviating from that best fit plane. The more the deviation, the more is the bumpy ride that you're going to get. And you can choose which neighboring cell configuration you want to apply here. I chose the nearest 8 neighbors or whatever that image signifies. Now, the good part, you have your core traversability estimation. You can fuse that with any graph-based SLAM, and it will result in very beautiful maps. And the Dragon Ball Z meme, obviously. So, performing global traversability estimation, this is how the global traversability map looks. You have a 3D LiDAR or a depth camera, and you have a UGV. You can run this. It happens in real time. Now, transforming your local maps into a global one involves 3 different steps. First one is a probabilistic update of your overlapping cells. The second one is linking your local maps to your SLAM's keyframes. In the sense, your SLAM's keyframes are optimized, so is your traversability map. You don't have to deal with any of the optimization on your end. The SLAM will do that for you. Then, routines in place to perform map cleanups or when SLAM has loop closures. Now, let's focus on how the local map fusion works. This image has 3 different robots, which signify 3 different keyframes in succession. And the overlapping cells have a probabilistic update routine going on, and that's how the local map is fused. You have a new keyframe, you compute the local grid, you update the global grid. And during optimization in your SLAM, if you have an updated keyframe, again you update the local grid and update the global grid again. So I thought about a lot before putting this slide into this presentation, but I thought some of you might be interested in it. Now, when I tried to build this algorithm, I wanted to make it SLAM agnostic, but that was a far stretch, and I was very, I couldn't do it because of the different theoretical implementations of SLAM, but I managed to make it graph-based SLAM agnostic. So the main problem when you try to do that is that any given SLAM can add 10s or even 20 keyframes in a very close proximity to each other, and computing local grids for all of those keyframes needs a lot of CPU, and you are going to overburden your system if you do that. Now, those keyframes are important for the SLAM because it needs to know where it's localized, but not for the actual map that you're trying to build. And using spatial hash grids helps you a lot in this sense. What you try to do here is you use the 6 metrics that any given pose gives you, x, y, z, and the roll pitch here. You pass it through a hash function, and that gives you a key to the bucket. And many different keyframes get accumulated in a bucket, and only one keyframe from each bucket is used. So regardless of any number of keyframes, only the most important one is used. And to decide which is the most important one, you can obviously define your own metrics. For me, it was how many connections does the keyframe make in your pose graph. Now, the good part is you can directly run this with nav2. You have your global traversability map, you project that onto an occupancy grid, and you will run just fine. It will run just fine on nav2. So now your robot doesn't have to worry about small rocks and pebbles, and it won't have a bumpy ride if you have your roughness hazard in place. Now, how do you maintain real-time mapping? The simple answer is you parallelize things. The first one, there are 3 different threads that run in this global mapping algorithm. The first one is involved in transforming your point clouds, and it caches them. And the second one is a local sliding window that moves with your robot and processes all the keyframes in your window. And the third one is the most important one, but also the slowest. It's the global adjustment. In case your SLAM goes through loop closures or new maps created, this will handle that for you, and it will slowly optimize your entire traversability map in the backend. Now, I'm running out of time, but let me show you quickly how you can integrate this with your SLAM. It's just 4 simple steps. You create an instance of your system, you push point clouds to the buffer, you add a new keyframe, and you update your keyframe. And that's it. This will do everything else in your backend, and you don't have to worry about anything. So obviously, as developers over here, we are so hungry to have good computational performance. And when I tried to measure this, I was pretty shocked myself because I compared it against the Octomap, and we are at least 5 times faster in the worst case scenario. And this was running on an Intel i9 on my comparison, but it would run just fine on an Intel i5 or an i7. You don't have to worry about it. This takes less than 2% of your CPU when you run it. And point clouds are computed in less than 15 milliseconds. Now, this is a simple experiment. You have a robot that's going round and round, and you have an Octomap. You have the Octomap's output. Now, you can see that the Octomap is all smudged up and smeared up because it doesn't directly depend on the SLAM, and your SLAM drifts over time, but your SLAM corrects itself because of the relocalization, but Octomap doesn't. Now, the traversability map looks fairly clean in comparison to the Octomap at least, primarily because it is directly dependent on your SLAM's pose graph, and as your SLAM's pose graph is optimized, your map is optimized as well. Now, how can you run this? I know a lot of you are eager. You just need to do 3 things: git clone, build, and launch, and it will run just fine. And I was trying to get the previous thing to 200 stars. I'm trying to get this to 100. So come on, please, guys. And this is released under the GPL v3 if you want to use it. So it's free, it's open source, and you can try it right here, right now, if you want. And I tried putting the ERC map because there are a lot of students over here, and a lot of you might have participated in the European Robo Challenge, and you can relate to this a lot better. This is the Mars yard, and this is the map generated. Now, I obviously cannot finish the talk without mentioning the beautiful place I work in. I really mean this. We are a very close-knit team, and we are very talented people trying to build real solutions that will come right to your home and keep your home tidy. We are hiring, and we are hiring across several domains: robot software engineers, perception engineers, embedded engineers, and even mechatronics engineers. Even if you're an intern, you can join us. If you think you're capable, please come and apply. You can visit this webpage, and if you don't find your role here, reach out to us on LinkedIn. And thank you from the bottom of my heart. It was an absolute pleasure presenting this to you, and hope you have a great time running this. And let me know if you face any issues. You can always open a ticket on GitHub, and I will be very active in replying to those as soon as possible.